Hi, I'm Patrick Morrison, and this presentation is about learning to read code as a technique for supporting students, teachers, and programmers. Dr. Gosdile said many interesting things when he spoke to us, but one that struck me in particular was about AP computer science teachers in Georgia. Good teachers can read and comment on code, but they write almost no code. Putting teachers in our existing computer science classes that are all about producing software, that's not the skill they need. I was reminded of a thread in discussions about learning to program that's been around for a long time. That learning to read code is an important part of learning to write code. Here's a nearly 30-year-old quote by Bill Gates describing part of his teenage hobby, learning about operating systems by fishing listings out of the trash. No Windows jokes, please. Robert Glass in Facts and Fallacies of Software Engineering said, "In learning any other language, the first thing we do is learn to read it. You get a copy of Dick and Jane or War and Peace and you read. You don't expect to write your own version until you've read lots of other examples of what skilled writers have written." Back to computer science teachers. I wrote to Dr. Gusdile and he pointed me to a column he'd written with more details about the teachers in Georgia. An external interviewer for Georgia Computes, their project to raise the level of computer science education in Georgia, interviewed a set of high school teachers of AP computer science classes and grouped them into successful and unsuccessful teachers based on the number of students they recruited into AP computer science, based on the pass rates of the exams, and how confident and satisfied they were being a computer science teacher. Unsuccessful teachers focused mainly on assessment. They taught computer science like they taught anything else in high school. On the other hand, none of the successful teachers ever talked about writing programs. They probably did some of that, but it wasn't a big part of what they did. They did use computer science specific techniques. They had students write code away from the computer. They had students explain code, talk their way through it. And Dr. Gusdile writes, "Studies like these give me hope that we can provide professional learning opportunities to existing teachers without trying to turn them into software developers. We mostly need to teach computer science teachers to read code." So the question that prompts for me is, can we find a way for people to wade into computer science rather than diving into the deep end of having to become a programmer in order to go teach other people how to program? Now, there's a case for, obviously, for being a programmer, but is there an easier way in, and so people could learn just as much as they need to suit their purposes? Dr. Gusdile had an earlier column, "Too Much Programming Too Soon," where he goes into a bit more detail about beginning with reading rather than writing. He references several studies in the literature on cognitive load theory, of which I'm picking one to emphasize a point about what's known as the worked example effect. In the mid-1980s, Sweller and Cooper performed an experiment in how people see and solve algebra problems. Their control group, well, all experiment participants saw a couple of solved algebra problems. Then the control group novices received 8 algebra problems and had to work their way through to solutions, where the treatment group were similar novices who received 8 problems worked out in detail, and they read them. Then they gave each group new problems, and the treatment group, the readers, solved problems in half the time with fewer errors. And so that would lead you to think that maybe lots of examples might be useful for teaching really any complex topic. Well, on the other hand, worked examples are not a panacea. At a certain point in learning, worked examples actually limit progress, and intermediate students do better with real programming and real problem solving. So the need to write code, the need to solve your own problems doesn't go away, but there is some kind of step before that where worked examples can be helpful. One of the other people Dr. Gusdile references very often is a man named Raymond Lister, whose primary interest is in the mental development of the novice computer programmer. And he and colleagues have spent a lot of time looking carefully at how novices learn to program, and they've worked to establish a hierarchy of skills underlying the ability to read and write code. They denote the idea of tracing, where if you're given a block of code, you can explain line by line what's happening, and distinguishing it from explaining, where given a block of code, you can summarize what it does rather than go line by line, then trace through the code. So, in a sense, seeing the forest instead of the trees, or not just the trees. So there does appear to be a gradient of steps. You learn how to trace through code, you learn how to explain code, that all supports writing code. And so some questions, maybe these are research questions. Given the observation teachers mostly read code and not write it, given that there appear to be a series of skills that precede and support writing code, here are some questions on my mind. Is reading code a separate skill from writing code? Would reading first education support teachers in conveying skills to students? Would reading first education support programmers in learning how to program? And how much leverage could we gain if we start by teaching how to read programs? Again, this is not a new idea, but I have three non-new ideas that might be suitable for trying to run experiments to see if they would help with reading. So, code reading basal readers like C-Spot Run and the Dick and Jane series that used to be used in American education, commentaries on examples of existing code, and then live programming environments. So the Dick and Jane idea, where you show pictures and you show simple sentences, is not a new one even in computer science. There was a little book, the little Lisper, that was written in the 70s and then followed on by the little Schemer much later. Actually walks through, teaches recursion through the use of Lisp or scheme in kind of a Socratic dialogue. Each page has questions on the left and then answers on the right, and you can read through the book to get an idea, and it builds up your knowledge of Lisp or scheme to the point where it can teach you about recursion, and then it builds up your knowledge of recursion to understand how to start and stop the process and when a problem fits with recursion. So it's not a new idea. It's a maybe a really valuable one. But so this example has already been tried in computer science in some ways. And one of the ideas that I had was whether we could apply that to more modern languages, C, Python, maybe Slither, C, Java, Perk, where we have, here I'm taking examples from Learn Python the Hard Way. It's a book, an online site and a book put together by a programmer to teach Python by having people type in programs and seeing what they do and then reason about it. But I was wondering if you just took, say, the program or program construct on the left page and then the output of the program on the right page, whether that would support teaching people how to read. For another example, commentaries. There's in the 70s, John Lyons, teaching his operating systems course, got a hold of the Unix source code back when, well, there was a point where it was hard to get, and there was a point before that where it was easy to get. Way back when, he got a hold of the source code and illustrated it, gave commentaries and explained details of the code that might not be obvious, and put it together in a book. And so annotating real existing code was another way that people learned how to read and think about code. Now, operating systems are kind of arcane. Maybe you would want to start with annotating Facebook quizzes so people can really see how they're made and maybe not worry about so much about what fierce animal they might be or whether they're OCD or any of the other things that a quiz will tell you these days. If they actually see that it's not magic and see how the quizzes are made, it might give them an avenue to understanding programming and maybe make them a little bit more comfortable about themselves. The third idea, learnable programming. This is Brett Victor. He's done a lot in the last couple of years, a lot of presentations that have received a lot of attention. And I don't have the video here. He has it on his site at the link below. But here he's not only he's taken a bit of code and he's annotated it, highlighted it, and he shows the output on the right, the code on the left, and then in between he's got a little diagram that shows the various loop levels that you're in and what the effect is of each statement, and you can walk through and see how the program changes. And it certainly seems like there's a lot that we can do with the technology that we have that goes beyond what can be done on the printed page. Figuring out how to use that seems valuable, but here we're not just looking at the output and seeing magic things happen, but we're looking at the details and seeing how, seeing the actual code and what each step takes. So there are some problems here that there are probably many more problems than what I have on the page here, but the first one I can think of is, should we focus on teaching the behavior of the physical machine? Like, for example, Donald Knuth does in his Art of Computer Programming. He actually develops an assembly, a fake assembly language to teach the details of how memory gets allocated and how space and time are traded off. And perhaps we should teach at the level of the physical machine. Perhaps we could teach at the level of a virtual machine, like the Java Virtual Machine or the Microsoft's Common Language Runtime. Perhaps we should teach at the level of the browser, because probably if you can master JavaScript, HTML, and CSS, there are a few intellectual challenges that are beyond you. Or perhaps there's some other representation that goes along with the output to help people understand where things are stored and how things are stored and how the computer is actually operating. So evaluation, reading, how do we evaluate reading before writing? How do we evaluate reading's impact on writing? I have some notes on control and treatment groups that I'm going to skip over here. I wanted to give a specific example. I was thinking about learning Python the hard way and about the primer, the Bazel reader that I had come up with, the C Python Slither. And if you could make it available online and have people log in, and certainly with the IRB's approval, record the people's views of the pages that they look at. And if you could have those people submit their Learning Python the Hard Way exercises, you could get a sense at a pretty fine-grained level of what gets read and what gets written and in what order. It would take some effort with timestamps, and you'd have to be careful in a number of ways to control properly. Maybe it's too hard to control properly, but I think there's an idea there for an experiment to understand how reading impacts writing in Python, and certainly similar exercises and primers could be designed for other languages. So, how much leverage can we gain if we start by teaching how to read programs? I don't know, but I think it's worth pursuing. So, in summary, reading may precede writing in programming, not just in human languages. If code reading supports teaching, interventions can be designed to better support teachers and their students. And if code reading supports code writing, perhaps there's more we can do in introductory programming courses. Thank you for your attention, and I look forward to watching your videos as well.